Okay, so today we're going to talk about section 6.2, or volume by cross sections. So some basic information. The area between the graph or equations provided represents the base of the solid. The cross section shape that we're given protrudes outwards from the base an infinite amount of times. And the volume of the solid is found by adding together all the areas of all the infinite cross sections. Also, another note. You may need to change the given equations depending on how your cross-section is perpendicular, meaning if it's perpendicular to the x or y axis. That way, you're integrating with respect to the right variable. So the procedure. Finding volume using cross-sections is similar to finding the area under the curve. Area under the curve can be represented by integral of a function. Meanwhile, volume by cross-sections can also be found by integrating a function that calculates the area of another shape, for example, a square. The side variable, or s, of s squared would be the equations that give the area between or under the curves. After setting up, the problem just becomes a simple integration problem. And an important part of volume of cross-sections is using the right area formula for the cross-section. These are some simple equations you should know, but most of them can be derived quickly and easily if you don't have them memorized. Remember that the s is the base or area under the curve, so when integrating, the variable should not be s, but x or y.
So for the first practice problem, we have that the base of the solid is bounded by y equals 2x plus 8 and y equals x squared, and that the cross-sections are equilateral triangles that are perpendicular to the x-axis. So the first step to approaching the problem is to identify the region that is the base by sketching the equations of the problem. So we can easily sketch these equations and see clearly where they intersect and identify that region as the base. So now that we know what the base is, we need to find the intersection points to find the bounds of the definite integral. So we'll set the two equations equal to each other, 2x plus 8 equals x squared. Then bring everything over to one side, so we have x squared minus 2x minus 8 equals 0. And then we can factor that into x minus 4 times x plus 2 equals 0. So x equals 4 and negative 2, and those are the bounds of the integral. So now that we have the bounds, we can determine the length of the base by doing the outer minus inner equations, or the equation that's further from the x-axis minus the equation that's closer to the x-axis. So we get that s, which is the length of the base, is equal to 2x plus 8 minus x squared. Now we'll get the appropriate cross-section formula. So we have a diagram of the equilateral triangle with all three angles at 60 degrees. And we have the height represented as well. So we can see that the sides are s over 2 and then root 3s over 2 as well. And area is 1/2 base times height. So we get that the area is s over 2 times root 3s over 2. Which can be simplified into root 3 over 4s squared, and then we'll substitute the value of s found in the previous step and get that it's root 3 over 4 times 2x plus 8 minus x squared, all squared. So now we just have to find the integral. So we'll use the bounds found earlier. So we have root 3 over 4 times the integral from negative 2 to 4 of 2x plus 8 minus x squared, all squared dx. We'll expand out the trinomial. So we get root 3 over 4 times the integral from negative 2 to 4 of x to the fourth minus 4x cubed minus 12x squared plus 32x plus 64 dx. And then the polynomial inside, when you integrate that, you get 1/5 x to the fifth minus x to the fourth minus 4x cubed plus 16x squared plus 64x plus c. So now we'll just use the fundamental theorem of calculus, and we'll do the capital V of 4 minus capital V of negative 2 and multiply that by root 3 over 4. So we'll be substituting both 4 and negative 2 into that polynomial. And then it's just a matter of some simple calculations, and we'll end up with the final answer of the volume of the solid being 164 root 3 over 5 units cubed. Now to a more difficult practice problem. We have that the base of the solid is bounded by x equals 4 over the square root of 4 minus y squared and y equals x minus 2. The cross sections are isosceles trapezoids with 60-degree base angles that are parallel to the x-axis. So the problem tells us that the cross sections are parallel to the x-axis, but we integrate with respect to the variable that the cross sections are perpendicular to. So if the cross sections are parallel to the x-axis, they're perpendicular to the y-axis. So we need to be integrating with respect to y in this problem. But first, we need to sketch the equations and identify the region that is the base. So again, we can clearly see what region is being described in the problem. Now that we have that, we can move forward and find the intersection points. We'll set the two equations equal to each other and see that it will actually require a lot of work to get through this algebraically. So we'll use a graphing calculator and find the intersection points y values to be y equals 0 and 1.6785735. Now we'll determine the length of the base again by doing the equation furthest from the y-axis minus the equation nearest to the y-axis, and we'll get that the base, which is s, equals y plus 2 minus 4 over the square root of 4 minus y squared. And again, notice that because we're integrating with respect to the y-axis, we had to isolate x in the equation y equals x minus 2 in order to use it to find the intersection points as well as the length of the base. So now to the next step, we need to again get the cross-section formula. So in order to derive this one, we need to realize that the isosceles trapezoid is really just 3 equilateral triangles. So again, we have that the base of one triangle is s over 2. So the height of the triangle must be root 3 over 4s. So for the area, this time it'll be 3 times 1/2 base times height, as we have 3 equilateral triangles. So we'll substitute what we know, 3 times 1/2 times s over 2 times root 3s over 4, and we'll get that the area is 3 root 3 over 16 times s squared. S was found to be y plus 2 minus 4 over the square root of 4 minus y squared, so we'll substitute that in and get that the area can be represented by 3 root 3 over 16 times y plus 2 minus 4 over the square root of 4 minus y squared all squared. Now we just have to integrate. So we'll be doing 3 root 3 times over 16 times the integral from 0 to 1.6785735. These bounds were found by finding the intersection points of y plus 2 minus 4 over the square root of 4 minus y squared all squared dy. And because this problem will require a bit of work in terms of expanding and then integrating, we'll be using a graphing calculator. And so in order to integrate on a graphing calculator, at least on a TI-84, you'll first want to press the math button and then the 9 button, and then enter in the 3 root 3 over 16 and the bounds of your integral, and then enter in the equation, and we see this long decimal that is our answer. We'll round it to the thousandths place, and we'll see that the volume of the solid is 0.143 units cubed. So that's all, and we hope you learned something from watching this video. Thank you. So for the first practice problem, we have that the base of the